These are the notes for AP Calculus on the topic of analyzing the graph of the first and second derivative. So here it says, let g be a function defined on the closed interval -8 to 9 with g of 2 equal to -1. So that's giving us one point we know on the graph of g is 2, -1. We'll use that later on. And then it says the graph of g prime, the derivative of g, so that's what this is, consists of two semicircles, let's see right here and here, and 1, 2, 3, 4 line segments as shown below. So with the graph of the first derivative here, there's a bunch of different things that it can tell us. So let's start with part A. It says find all the values of x, all values x at which g has a relative maximum. We're looking for all the x values. G has a relative maximum, and then it asks us to justify our answer. So remember, relative maximums are when the first derivative changes from positive to negative. So we're going to draw our number line here, right underneath the graph that represents the first derivative. Whenever you have a number line, make sure you label it. In this case, it's g prime of x. And since this is the graph of the derivative of g already, whenever the graph is the same as what your number line is, you're going to look at the y values. Because this is the derivative of g prime already. So basically above, below the x-axis. You can see it starts out with positive y values until we get to -6 right there, which is 0. And then it stays positive all the way until 0, where it's 0 again. And then it's negative all the way until 5 to 0, and then positive until we get to 9. With 0 again. All right, so we're looking for relative maximums. And notice here the sign doesn't change, here the sign changes from positive to negative, so that's a relative maximum for the first derivative. And this would be a relative minimum. First derivative changes from negative to positive. And this shows us when g of x, first derivative is positive, you know g of x is increasing, negative, because the first derivative is the slope, g of x is decreasing, and back to positive, back to increasing. So in this case, we only have one relative maximum. So we can write that down. And say g has a relative maximum x equals 0. And what we justify our answer here is since g prime of x changes from positive to negative at. All right, let's take a look at part B. Says for -8 to 9, find all the values x at which g has an inflection point. So inflection points are when the second derivative changes sign. We'll answer here too. So now we need a number line that represents the second derivative. So go back to our graph here. And let's draw another number line. And directly under the graph, this time it will represent the second derivative rather than the first. So label it g double prime of x. And the second derivative, since we have the graph of the first derivative, is the derivative of the first derivative, or the slope of the first derivative. So now we're going to be looking at the slope of g prime to determine what g double prime is. We can do the slope that's up being negative until we get to -6. But in -6, we've got a corner there, so the derivative or slope does not exist. Then the slope is positive all the way. We know it's right at -3 there because it's a semicircle. That's exactly halfway in between this word level off between -6 and 0. So the slope is 0 there. Then it's the positive slope there. Then back to negative slope until we hit 0. Another corner. It does not exist again. Then the slope is negative. It stays negative until 2. Got another corner, so it does not exist. And then the slope is 0 all the way until 4. Another corner that does not exist at 4. Then it's positive until 5. We hit another corner where it does not exist, and then we've got another semicircle. So it's positive halfway between 5 and 9 is 7. So it levels off with a slope of 0 exactly at 7, and then back to negative until we get to 9. All right. So now we're looking for where it has an inflection point. So that's where this, well, let's write down what this tells us about g of x. When the second derivative is negative, that means g of x is concave down. Positive. Second derivative positive means g of x is concave up. So concave up, concave down, concave down. When it's 0, that means it's not concave up or concave down, which means it's a straight line. So this section is linear. And then back to concave up, concave up, concave down. So we're looking for where it changes concavity, where the second derivative changes sign for points of inflection. And see that happens at -6. Even though it doesn't exist, that still is a point on the original function, because the first derivative exists everywhere along here from -8 to 9. So we know the original function would also have to exist there. So we've got one at -6, another one right here at -3, where the second derivative changes sign. Another one here at 7. So those are only 3 places where the second derivative changes sign, from positive to negative or from negative to positive. So -6, -3, and 7. Those are the x values. So we can say g inflection points. -6, -3, and x equals 7. And your justification would be since g double prime x changes sign, you could list them all, or you could just say at these points. There's All right, next let's take a look at part C. It says find all the intervals this time on which the graph of g is increasing and concave down. So those two things happening simultaneously. So increasing and concave down. Increasing is when the first derivative, g prime of x, is positive and greater than 0, and concave down is when the second derivative, g double prime of x, is less than 0 or negative. So we're looking for the first derivative is positive and where the second derivative is negative. And if you line up your number lines, you can see where that's going to happen. First derivative positive, second derivative negative. Notice that happens right here, from -8 to -6. Also from -3 to 0, increase and concave down, and also from 7 to 9. So those would be our 3 intervals there. The g is increasing and concave down on -8 to -6, -0, kind. And then you're just explaining your answer, explain your reasoning. It would be since g prime of x is greater than 0 and g double prime of x is less than 0. You could list on and list the intervals, or just say on these intervals. All right, now let's take a look at the last part of this one. Part D says sketch a possible graph of g on axes provided below. So remember, we knew 1 point on our graph, 2, -1. So let's start there. You know it has to go through that point. And let's first move from right to left using both number lines there. And stop the graph each time something changes. So notice from 2 to 4 we know it's decreasing and it's linear. So this is a straight line. And we can tell with a linear graph it has a constant slope. We can tell the first derivative on this interval right here is exactly equal to -2. So that's the slope. First derivative equals -2, so the slope is -2 from 2 to 4. So we can graph this section pretty accurately. We know it's linear, so it goes down to right 1 and down to right 1. And then you can line up your ruler there. So we got that section graphed, a linear section with a slope of -2 exactly. Okay, then let's go back to our number line and see what happens after 4. Then next time something changes is 5, so this little interval from 4 to 5, it's still decreasing, but now it switches to concave up. And remember, our first derivative exists everywhere here. So that means the original function should not have any corners or cusps. It should be a nice smooth curve. Otherwise, if it had a corner or cusp, the original graph of g that we're graphing, the first derivative wouldn't exist here. There'd be like a vertical asymptote or a hole somewhere, and we don't see any of those on the first derivative. So it should be a nice smooth curve. So decreasing concave up shape. So here you just have to transition from the linear section into decreasing concave up. And remember, we don't know any other of the y values exactly here, so we're just going to get the increasing, decreasing as a possible graph. The other points for sure certain besides these three. Just going to try to make it a nice smooth transition, decreasing concave up until we get to 5. We're just going to exaggerate the size of that point at 5 just to show something's going to change. So notice I leveled it off because at 5, see how the first derivative is 0? Then from 5 to 7, it's increasing concave up, shaped like a cup. So from 5 to 7, increasing concave up. And we don't know the y value for certain, shaped like a cup. And then 7 to 9, increasing concave down. And this is the level drop at 9, so increasing concave down, shaped like a frown until we get it. And again, we don't know these y coordinates for certain. Just the shape of it should be. Now going backwards is a little trickier because of the increasing, decreasing. You've got to be careful. Your increasing, decreasing always refers left to right. So from 2, the next time something changes is 0. From 0 to 2, it's decreasing concave down, shaped like a frown. And it's got to be a nice smooth transition into this linear section. So decreasing concave down. So in order to decrease and end up here, we have to start somewhere above it, right? And decreasing concave down, shaped like a frown, something like that. Smooth transition into the linear one as much as possible. Then, again, don't worry about the exact y coordinates. Then from -3 to 0, -3 the next time something changes, it's increasing concave down, shaped like a frown. So in order to increase and end up here, it has to start below it at -3 somewhere. Increasing concave down, shaped like a frown. Again, I'm just exaggerating the size of these points where something changes. Then from -6 to -3, it's increasing concave up, shape like a cup. Increasing concave up. And then finally, from -8 to -6, increasing concave down, shape like a cup. So there's a sketch of a possible graph of G. Again, the only points note for certain are in this red section where it's linear, because that's our starting point, G -1. And here we need the exact slope. Here we're just estimating based. We should know the shape of it, but we don't necessarily know the exact y values of the green part. So those are some different things you can be asked about with the first derivative. Now let's take a look at analyzing the graph of the second derivative. This one, there's not as much you can figure out, but there are some things you can tell based on the graph of the second derivative. So the graph of the second derivative, it asks us, well, first it says graph above represents f double prime, the second derivative of the function f, from -8 to 8. And A and B are asking about the intervals on which the graph of f is concave up and concave down. So we're going to draw our number line right underneath this graph. And label it f double prime of x. So this is the second derivative. And again, whenever the graph is the same as your number line, you look at the y values. So you can see the y values here are negative until we get to -5, 0, but then they stay negative until 0, positive until 6, and back to negative. So it's again above or below the x-axis. And this tells us that f of x, when the second derivative is negative, again concave down, still negative concave down, positive concave up, negative concave down. So where f is concave up, there's only one interval from 0 to 6. And it doesn't say to justify. If you did, you would just say since f double prime of x is greater than 0 on this interval. And the intervals on which the f is concave down be -8. And because this is 0 at -5, you don't have to stop the interval. If it doesn't exist, then you would. But you can go all the way to 0. And then also from 6. And this also shows us, for part C, what values of x does f have a point of inflection, and this will justify your answer. So points of inflection, again, are where the second derivative changes sign, because the graph changes concavity. You see that it doesn't change sign at -5, but at 0 does. And the second derivative changes sign at 6 as well. So there's 2 points of inflection at 0, x equals 0 and x equals 6. So you can say f has points of inflection, same thing as inflection points. 2 different ways of wording it. Points of inflection. X equals 0 and x equals 6. And your justification would be since f double prime of x changes sign at x points. Or I could say at x equals 0 and x equals 6. And that concludes the notes for AP Calculus on the topic of analyzing the graphs of the first derivative and the second derivative.